All right, in this lesson, we are going to look at the concept of molecular polarity. And we talked about this a little bit in the last lesson with water. First off, it's important to note molecular polarity, only important concept for covalent molecules. So any sort of ionic molecule where electrons are being transferred, this isn't something you'd have to worry about because um, once electrons are transferred, the structure changes. And as I said, um, ionic molecules are like ultra, super, mega polar molecules because it's not that there's an imbalance between how the two atoms are pulling electrons, but it's that one atom has definitely won the tug of war and the other one has given up. So that basically makes them like, uber covalent if you want. But that's just what ionic means. Now, a lot of covalent molecules have many different atoms in them. And you notice with water, for instance, there were 3 atoms, and we had to assess the covalentness, that's a word, of both of the bonds. And that helped us determine that there is kind of like a cloud of negative-ish space up here and a cloud of positive-ish space down here because the electrons are being forcibly pulled towards the oxygen and pulled away from the hydrogens. And that gives it a partial negative charge at the top and a partial positive charge at the bottom. So because of that, we can draw the molecule's overall polarity with one large partial change line. The bottom of the molecule has an overall positive charge, as I said, and the top of the molecule has an overall negative-ish charge. So that gives the molecule an overall polarity that looks like this. It's basically moving from the bottom up or from the bottom up. Obviously, this entirely depends on what orientation you draw the molecule, right? So if I were to draw my water like this, for instance, well, my polarity is going to look like that instead, right? It all depends on what the orientation of the molecule is when you draw it. Um, so obviously you have to adjust for that. We're going to look at 4 molecules and determine what their overall molecular polarity is. Let me just fix the page up and we'll get right into it. Okay, so the first 2 molecules we're going to look at are very similar. One is ethane and one is ethanol. Now, ethane is a common fuel. Ethanol, also a common fuel, additive for gasoline, also the active ingredient in drinking alcohol. Um, Ethane, really, its main purpose is to just burn it and collect heat. Um, Now, these 2 molecules are going to have completely different polarities, even though the only big difference here is just that one little oxygen that is in ethanol that ethane doesn't have. So the first thing we have to do is calculate the delta ENs for the bonds that are here. So this molecule here has carbon-hydrogen bonds. Delta EN for carbon to hydrogen is, let's see, is 2.5 for carbon, 2.1 for hydrogen. That gives us a 0.4. And 0.4 it falls in the nonpolar covalent range. Now what this means is that the bonds between carbons and hydrogens does not produce a polar molecule. And that's quite interesting because most organic molecules are absolutely packed full of carbon-hydrogen bonds. That's why we often refer to organic molecules as hydrocarbons, because they're full of hydrogen and carbon. But the bonds between the carbon and hydrogen don't actually provide any polarity. And this is another reason why organic molecules tend to be non-soluble in water. I know we haven't talked about solubility yet, but the general rule with solubility is a polar solvent, like water, can dissolve polar solutes, like not ethane. So since ethane basically is completely non-polar, and how do you show that? Well, I mean, that's pretty much it. You just write non-polar on it, and then that means it's non-polar. There's no delta pluses or minuses to show in this molecule, so there's really no point in putting those on there because there's no imbalance in electron transfer. Now, the difference is that in this molecule, we have a carbon oxygen and a hydrogen-oxygen bond. So I'm going to have to find the change in electronegativity for those. So let's do carbon-oxygen first. Okay, oxygen's 3.5, carbon's 2.5. So that gives me a 1.0 there. And that is a polar covalent bond. So I should be able to put a delta minus and a delta plus on this and draw that. And then we can do the exact same thing for the oxygen-hydrogen bond. And we already know that the oxygen-hydrogen bond electronegativity is 1.4. Don't worry, that's a number you'll probably get used to, especially if you do a lot of these. So that puts another delta positive and delta negative here. And what does this do? Well, it creates an overall polarity in this molecule that goes towards that oxygen. How you draw it is really up to you. There's a lot of different configurations for this because that oxygen could be here, 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 here. But, I mean, I would just kind of draw it like this, I guess. Delta minus, delta plus. So what you're going to find is you have this sort of like huge area over here of mostly nonpolar molecule, and then just this little bit of polarity here where electrons are being pulled up towards the oxygen from two directions. Now ethanol, definitely soluble in water. That's why it's so easy to mix into our alcoholic beverages when and if you guys ever get to the point where you do that. So ethanol, soluble in water because of that little bit of polarity right there. It's able to dissolve and jump right into those water molecules. The last two molecules we're going to look at are ammonia and boron trichloride. Now you notice I put a little note at the bottom there, especially with covalent molecules, as you guys know from Unit 1, they can have lots of atoms, and the atoms can be in all sorts of interesting configurations and arrangements. So, as it says, when in doubt, punch these things into the internet. Make sure that if I ask you to find the polarity of a molecule, that you know what it looks like. Generally, I'm going to give you the molecules. You guys remember I said I don't really expect you to be able to draw these this year. You'll learn about it next year on where these shapes come from. There's a reason why ammonia has this shape, and the hydrogens all are pushed down by the non-bonded electrons at the top. It's actually very similar to why water pushes the hydrogens away from itself. So what we have to do, as always, find the delta En. Okay, this time we have nitrogen and hydrogen. Let's see, what's nitrogen's electronegativity is 3.0. That's pretty high. Hydrogen's 2.1. Here's a number I'll never forget. So that gives me 0.9 or polar covalent. So that means that because it's polar covalent, I can put my delta minuses and pluses onto my molecule. Okay, and that means that this hydrogen's electrons are moving towards the nitrogen, so's that one, and so's that one. So the hydrogen, or sorry, my apologies, the electrons are moving towards the nitrogen, and that creates an overall upward polarity. Again, I call it upward, but it could easily be downward if you just drew it the other way and put the hydrogens going up. Doesn't really matter. You use whatever configuration you're given or whatever you find. The last one is boron trichloride, which is BCl3. Again, we need to start by calculating delta En. All right. Now, boron is actually a metalloid, which means it can act like a nonmetal and it can act like a metal. But in this case, it's forming a covalent compound, so electrons are being transferred. My apologies. In this case, it's forming a covalent compound, so the electrons are being shared. Chlorine has an electronegativity of 3.0. Look, that's the same as oxygen. They're both very... My apologies. That's the same as nitrogen. They're both pretty good at pulling electrons. And boron has an electronegativity of 2.0. So that gives us a delta En of 1. And That means exactly as you'd expect, you've got the chlorines essentially pulling electrons away from the boron in all three directions, right? That chlorine's, it's like a tug of war with boron in the middle, and he's got three opponents pulling electrons away. But the question here is, what is the overall molecular polarity? And this is where stuff gets interesting. This molecule actually is not polar at all. Isn't that crazy? Boron trichloride is actually completely non-polar, even though there are three different instances of atoms pulling electrons away from that boron. The shape of this molecule is called trigonal planar. And what that means, it's a flat molecule, and it's exactly a 120-degree angle in between each of these bonds. So the three poles in the three different directions essentially cancel each other out, and you end up with a molecule that doesn't have any actual polarity. I don't know if any of you guys have done vectors or anything yet, but if you were to basically add these three vectors together, so you'd have the one going up, you'd have the one going down and to the right, and then you'd have the third one going down and to the left, and you'll notice that you end up in the same spot you started, which means basically these three forces are canceling each other out. So this is actually a non-polar molecule. But that doesn't mean a non-polar molecule can't have polar bonds inside. So it's a non-polar molecule with polar bonds that essentially cancel out. All right, that's it for this week's lessons. Next week, we're going to look at water, solvents, and get into some other new stuff then. If you have any questions about the content here, please do drop me an email anytime. Check out some of the review questions. Whatever you need, I'm here to give you a hand. Enjoy the rest of your week, and hopefully we'll talk to you soon. Oh, and sorry. As you guys know, there's no quiz this week. So don't email me looking for a quiz. We'll get back into quizzes next week, probably. I don't know. I'll figure it out. Stay tuned on email, and we'll get there. Have a great rest of your week, everyone.